here Galois extensions are to be characterized, so we will look at normality first. We take an algebraic extension and call it normal if for every element alpha in E, the minimal polynomial of alpha over f splits over E. So for example, algebraic closures are normal extensions. Here's an example of a normal extension. The reason why this is normal as an extension can be seen through the next characterization of normality that we will present here. Basically, this extension is normal because the overfield here is the splitting field of the irreducible polynomial x squared plus 1 over q, which is a property that characterizes when a finite degree extension is normal. On the other hand, this extension fails to be normal because x cubed minus p is irreducible by Eisenstein's criterion, and this is one of the roots there, but this guy, which is another root of this polynomial, is not contained in the extension. Once again, the current question is when a finite degree extension is Galois. So you take a finite degree extension, okay, and assume that it is normal. Since it's finite degree, E is obtained by extending f by a finite number of elements in E, say alpha 1 through alpha n. Okay. Now, because of the normality of the extension, each of these polynomials splits over E, and so does their product. And clearly, E is then a splitting field for this polynomial h over f. So if an extension is normal, finite degree extension is normal, then the extension field is a splitting field for one polynomial over f. Going in the, reversing this argument, it's interesting to see that for this property to be satisfied by E, namely E being the splitting field for a single polynomial in fx, is sufficient for the whole extension, the finite degree extension of f to E, to be normal. Let us see this. So we are assuming E is a splitting field for some polynomial, doesn't have to be anything specific, and you take a minimal polynomial of an element alpha in E and call it f. We can find a splitting field L, say, of f over E, so we have this. Then L is generated by E and the roots of f. But then E is generated by f and roots of G, which when combined yields that L is generated by f and the roots of G times f. Okay? So in the end, L is a splitting field for some polynomial over f. Remember what we did in our previous video. When this happens, then the action of the Galois group of L over f on the roots of f yields a single orbit. So it's a transitive action on those roots. That means for any beta in L of f, for any root beta in L of f, you can find a homomorphism and an f automorphism of L, that takes alpha to beta. But you know what this says then? Since E is a splitting field for a polynomial over f, and alpha is an F automorphism, F isomorphism on E, or let's say its restriction is an F automorphism from E into L. Therefore, its image is again a splitting field for the same polynomial over F over the same fixed field F. And well, so this means what? This means we have inside L two splitting fields for the same polynomial, say G. But there can only be one. So we must have phi of E equal to E. That means the root beta must be contained in E as well. So all roots of F are in L are also inside E. Therefore, F splits over E. And to summarize what we have proved that a finite dimensional extension such as this is normal if and only if the extension field E is a splitting field of a polynomial over F. So this characterizes when a finite dimensional extension is normal. Finally, let me remind you of the exercise or the question that I posed at the beginning of this discussion, or somewhere close. That question was, can two non-associate irreducible polynomials over F have common roots in any extension of F? Well, to give you a spoiler, the answer is no, but it's left to the Weber to prove this. Well, the second question is rather easy because we already gave the answer at the beginning of this video. But there's only one detail that needs to be filled in by the Weber. So see you in the next video. Thanks.